In today's lecture, we are going to learn about the limits for multivariable functions. Well, they turn out to be quite similar to the limits for single variable functions that we learned in Cal 1. By the way, it's a typo right here, so please cross this out and change it to single variable. Single variable. Alright? When we talk about multivariable functions, we talk about function of x and y. F of x and y, and sometimes we talk about function of x, y, and z. You can add more variables to these functions, but in this course and in this lecture, we usually keep the number of the variables to just 2 or 3 to keep it simple and easier to understand. Back to this slide, single variable, of course it has to be f of x. As I told you, limits for multi are quite similar to the limits for the single, but they turn out to be a little bit more difficult and trickier when it comes to finding the limits values and to prove the existence of the limits. In order for you to really understand the concept of the limits for multivariable functions, it's important that you fully understand the definition of the limits for single variable function. So I'm going to need to spend some time right now to mention about something that you learned long before, maybe in high school or maybe in Cal 1. This is about the definition of limit for a single variable function. Here's my version. So we are talking about this single variable function fx, and we want to know about this limit when this fx with x approach a certain value. Of course, when it comes to limit, there's something approaching a certain value, and we call that number x0 right here. We want to know the definition of this, but before I talk about that, let me ask you one very important question. Does this limit mean the same as the function value at x equal to x0? Can you follow me? Does this limit mean the same as the function value at x equal to x0? Let me write that down. Means the same as function value at x equal to x0. And by the way, this is a question, not a regular sentence for you to memorize. Does this mean the same? All right. I'm pretty sure that many of you, once you read this sentence and you know right away, no, it's not the same. There is a difference between the limit and the function value. So write a big no right here. No, all right? Doesn't mean the same. Now, here is the definition for the limit, and I'm going to give one for the function as well. Limit of fx when x approach x0 means function value, right? Function value when x is really, really close to x0 is really, I want to add another really right here, but one is enough. Really close to x0. So the key word is right here. The key is being really close. Now what about function value at x equal to x0? This, just like it says, function value when, all right, when x is exactly at x equal to 0. Oh, sorry, exactly at x0. Exactly at x0. So here's the difference. A small difference, but they are different. Okay, one is exactly at that point, and the other is about being really close. Oh, by the way, keep in mind that even though they don't mean the same thing, they can have the same values. You might wonder, what does that mean? Doesn't mean the same thing, but have the same value. So let's take a look at this example. So I have this fx right here, a very basic one, basic function x plus 2. And I can find the function value of this at x equal to 2. F at x equal to 2, it's going to come out to be what? 4, right? Even very easy one. And of course, I can find the limit of this function when x approach 2. Limit of fx when x approach 2. And as you can see here, when we find this limit, it comes out to be 4. And they are the same values, but they represent different things. One right here, limit, is about something that is close to x equal to 2, but this function value right here is exactly there. Alright? Now you know the difference between these two. Let's focus on this word. Really, really close. What does that mean? Really close? In order to understand this, we need to graph it. So let's use some graph to explain about this more. Here we are working with single variable functions, so we only have one variable to change. So I'm going to use just one axis right here, and it's going to be x. And of course we have this one very important point, x0, which we try to approach. I'm going to put it right here. Alright. Now we are going to try to be really close to this point. In order to be really close, we have to approach it. Let me approach this x0 point maybe from the left hand side. I'm going to approach it like this, and I'm going to stop just before I get there, because I don't want to be there, I just want to be close. So let me stop it right here, and I think it's close enough. You can go a little bit closer if you want, but for me this is fine. It's really close. Okay. And as you can see here, when it comes to approaching this x0, I have another choice too. I can approach this point from the other side, from the right hand side. So I can approach from this side, and then I stop right before I get to x0. And I think this is close enough, and I have this point right here. And as you can see here, we have two ways when it comes to approaching this same point. So we also have different notations for these two limits as well. So on the left hand side, this is approaching, right? It's about the limit of fx when x approaches x0. But then we know that this approach from the left hand side, we approach from the negative side of the x value, coming from the negative infinity. So we are going to add this minus sign right here to remind us that this is a sublimit coming from the negative side of the x value. Alright, and since this is on the left hand side, we can call this left hand limit. Alright, now as you might have guessed, we are going to have something similar on the right hand side. On the right hand side, this is approaching as well, so this is limit of fx when x approach x0, same point, but here we approach from the positive infinity, right, from the right hand side, so we put this positive sign to remind us the direction. And as you can see, this is coming from the right hand side, so we can call this right hand limit. Alright, now that you see what's going on in the space here, let's talk about the definition of the existence of a limit. So here is the definition of the existence of the limits. Existence of limits. Okay, limit of fx. Alright. Now I am going to give you some definition right here. So let's write down this. Limit of fx exists at x equal to x0 at a certain point when. Alright, here comes the condition. And I'm going to write down as red right here, very important. When the left hand limit and the right hand limit are equal. Here's the key, right? When the limit, left hand limit, which is limit of fx, when x approach x0 from the left hand side, which is negative, must be equal to the limit from the right hand side, which is this fx, x approach x0 from the positive infinity. So it requires both sublimits to be equal, right? You can say that this is left sublimit and this is right sublimit. Okay, so please put a box around this because we are going to refer to this again. This is the definition of the existence of the limit at a certain point. Okay, now that we are on this subject about the definition of some property, let's talk about continuity. So let's add a note right here at the bottom. Continuity, all right, continuity of a function at a certain point. Continuity of function fx at x equal to x0. Alright, so let's write that down here. Fx is continuous. I hope I have enough space for this. Continuous at a certain point right here, x equal to x0, when, and we are going to have some conditions right here, right? And it turns out to be quite exactly the same as the one above. So let's bring that down here. This part is exactly the same. Limit of fx, x approach x0 from the left hand side equal to the limit of fx when x approach x0 from the right hand side. Well, they turn out to be exactly the same here, but we need to add one more right here. And these two need to be equal to the function value at that point. Function value at x equal to x0. Now let's put a box around that. They are quite similar, except that continuity has one more equality when it comes to these conditions, which is this: the function values play a part in this definition too. Alright, now that we know the definition for existence and continuity, let's expand this to work on the multivariable functions. So I'm going to expand this definition of existence of limits to a general form. So here is the general form. General form, general existence of limit. Alright, and we hope that we can use this on the multivariable functions. Alright, so let's make a note right here. Limit of a function, and this should apply to multi, should apply to single as well, to any function. Limit of a function exists, alright, when, right here is the condition, all sub or directional limits are equal. Alright, here's the same thing. What you look at right here, they are subdirectional limits and they are equal. Right, so we expand this to work on any limits. So we require this all subdirectional limits to be equal. Here's the keywords. All subdirectional limits are equal. Okay, so let's make a box around that again. It's all about these small directions that they have to be equal. So let's take a look at this, what this means in one dimension. In one dimension, I want you to take a look at this figure. Alright, we only have the freedom on one dimension, on one axis, right? So all directions mean left and right. So when we work with one dimension, we only have left and right, and that's all. The question is, what about we work with two dimension? What do we have here? Alright, so let's take a look here. In two dimension, we want to find the limit of a multivariable function. For example, f of x and y. Here we have two, and then we are going to approach a certain point. X, y approach this x0 and y0. Everything is exactly the same as before, except that here we have y. So what does this look like in the space? So let's take a look at this simple graph right here. So here we are going to have two axes instead of just one, because we have the freedom to change x and y. And we have this important point x0 and y0 in the space. Alright, this is y, this is x, and let's assume that this x0 and y0 is right here. Alright, and we are going to try to approach this point. Before we just do left and right, so we can do that again. We try to approach. By the way, we want to approach to be very close but not there. Same concept. What about we approach from the left hand side like before and we stop right here? And we can do the same thing, approach from the right hand side. This is left. Oh, sorry. This is left and this is right. And we can approach from the up here, from upward, up, and we can approach from down here, downward. Is that all? It's not so simple, right? It's not just adding up and down and that's it. We have other directions in the space. For example, here, coming from an angle of 45 degrees, here, 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 all of these are directional and sub-limits. And even more, we have lots and lots of them. Okay, so we can make a note right here that we have infinitely many directional limits. Make a note right here that in 2D, in 2 dimension, we have infinitely many subdirectional limits. Infinitely means a lot of them. Infinitely many subdirectional limits. Alright, well, we have a lot of them, and it turns out that in order to prove the existence, we have to prove that all of them are equal. We come back to this. All of them have to be equal for the limit to exist, which means that we have to, well, check them all. Have to check them all. That's why I told you that when it comes to multivariable functions and the limits, it becomes a little bit tricky to see the existence. We have to take a look at all of them and to see whether they are equal. Now let's move to the next slide. Okay, here we want to find the limit of multivariable function of x and y, and of course we are working in 2D space, so this we have the approaching in 2D to this point x0 and y0. Okay, so let's put this point in the figure, which is already there, which is right here. Alright, this point is x0 and y0, and we want to approach this point to be just really close but not there. And as I told you before, that we can approach from many different directions, which means that we are going to have lots and lots of sublimits to check. Okay, lots of sublimits, and that is the first difficulties. Well, what about I put it down here? I'm going to make a conclusion right here about why the limits of multivariable functions are a little bit trickier. So here is the difficulty. Let's make a conclusion right here. Difficulty of limit of f of x and y. Okay? The first one is the number of the subdirectional limits. Number one is the number of sub, or you can say directional limits. We have lots and lots of them, and we need to check them. That we need to check. Alright, so as you can see here, lots of angles that you can approach this x0 and y0. But it turns out that this is not the only difficulty when it comes to the limits of multivariable functions. We have number two. it turns out that it's not just about the numbers, it's about how you approach the point as well. So let's take a look here. This is about how you approach the point. So I'm going to write the same graph. All right, let's assume that it's the same graph. And we have this x0 at the same point, somewhere around here. Before we approach this point by using a straight line. So what you see on the left hand side is a straight line approach. All right, and it turns out that you can approach this point differently, like using a parabola, like this, approaching with a curvy trajectory, and something like this, and maybe a little bit narrower, or maybe a little bit wider. All right, so here we are using parabolic curve in order to approach this point, and it turns out that it matters too. When you change the way you approach it, sometimes it causes the final limits or sublimits to be different. So here, parabola. All right, and not just this one. You can approach it differently, like using the same parabola but on the side. Okay, I need to draw it again. I don't want to make a mess. Alright, same point right here, x0 and y0. And you can approach this point from the side, parabola. Alright, and maybe more, but I think you get the idea. It's about how you approach the point. And there are many different ways. Many different ways. So what you see right here, this is parabola. And not just these two, not just straight line and parabola, we still have quadratic. Other quadratic curve. And you can use exponential to approach this point. Exponential. And you can use the logarithm curve to approach this point. Logarithm. So as you can see here, many different ways in order to approach this point, and each way has infinitely different directions to consider. So here, the second difficulty, many different ways. To approach. Alright, x0 and y0. And the way you approach matter. It can cause the difference in the end. And here are the difficulties. The number of the path. Oh, by the way, sometimes we call these directions, many directions, as path. Well, I should say paths. Alright, because we have lots of them and we have lots of paths here. And same here. And we need to check them all the paths, all the different ways, and then prove that they're all equal in order to guarantee the existence of the limits. Make a big note right here, need to check them all. In order to guarantee the existence of the limit. Alright. But the good news is, in the next couple of slides, I am going to give you a guideline or a procedure for you to follow step by step. That way you can use it to find the values of the limits or to prove the existence of a limit without getting overwhelmed by all these directions that you have to consider and check. But before that, let's take a look at the next slide first. In this slide is about the properties of multivariable limits. And to me, these are quite the same as the ones for the single variable limits. So let's take a look at this really quickly. The first one here, the sum rule. And let's take a look at the difference rule all together along with the product rule. So what they say right here is that if you have an operation between two functions like this, f plus g, or f minus g, or f times g. And if you want to find the limits of these operations, what you can do here is to distribute the limit to each of the functions directly and separately, like this. This limit at the front can go to f directly, and then you get this value of L right here. This same limit can go to g directly, and you get the value of m, and then in the end you can perform the plus right there. Same with the subtraction. Limit at the front can go to f and g separately, and then you get this L and m, and you perform subtraction right at the end. Same, of course, same with the product. Limit goes to f and g, and of course you see this product right at the end. As you can see here, this is quite the same as what we have learned long before, maybe in Cal 1 or maybe in high school. I don't know about that, but one thing for sure is that all of these properties, we already know about them. So let's not spend too much time here. Let's move to the next one, which I find quite important because this is about the procedure for multivariable limits. Once again, this is a guideline, which means that I do not force you to follow this strictly. It also means that you have the freedom to try on your own way. You can try your own method. You can try your other ways of solving the problems. You can improvise the way you want. But in the end, if you find yourself getting stuck or getting lost and do not know what to do, you can come back to this guideline, and maybe it's going to help you and makes your life a little bit easier. Alright, let's take a look at this procedure for multivariable limits. So when it comes to finding a limit, this number one right here is the first thing I always do. The first thing is try substitution. So I'm going to put direct substitution right here. Direct substitution. So let's put an example right here. Let's say that we have this multivariable limit, f of x and y. And we want to find the limit of this function. And of course, when it comes to limit, the value of the variable must approach a certain value, like this, xy approach x0 and y0. Sometimes, when you apply the direct substitution to this function, you get the limit's value right away. So when this direct substitution is successful, this is the case when this is successful. Success. It turns out that this limit value is going to be the same as the function value at exactly x0 and y0. As you know, this is about the value of x and of the function when xy is really close to x0 and y0, right? So why don't we just use them and put it right in the function, and maybe we get that limit values right away. The answer is right there in front of you, and that is when this substitution is successful. But keep in mind that this substitution technique doesn't always work. Sometimes you get something that is different, and this is when it fails. Alright? This is the case when substitution fails. And when it fails, you are going to get something like this. 0 divided by 0. Infinity divided by infinity. I am pretty sure that you have seen these kind of forms. So let's put a name over them. Right? These kind of forms are called indefinite. Indeterminate. Alright, indeterminate. Indeterminate means that you cannot determine anything about these two. You don't know its values. They are not 0. They are not infinity. You don't know the conclusion about these two terms. So in the end, it also implies that when you see something like this, something indeterminate like this, you are supposed to try something else, right? So that's when we move to some other technique. And I'm going to put number 2 right here. Since the direct substitution failed, we are supposed to try this new technique. And right here, it's called manipulation of the function. But personally, I don't like the word of manipulation, so I'm going to use my own term right here, which is rearrangement. If substitution doesn't work for me, then I try to rearrange my function. Rearrange the function. The question is, why do we need to rearrange it? Because sometimes the original form is indeterminate, but by rearranging your function, maybe you can get some elimination of some terms, and then after the elimination, then your function turns out to be determinate. All right, so rearrange has the point here to eliminate some factors. Right, rearrange the function to eliminate. The keyword is right here. Some factors. And after the elimination, we hope that, well, we can find the values out of them. Okay, so what kind of techniques that we can use to rearrange the function? Let's take a look at the first one here. Number one, factorization. All right, you know about this. Sometimes the original form of the function has the form of the polynomial. And then you perform some factorization, and it turns out that the factors that you found can cancel with the ones at the denominator. So your function looks better after that. That can happen, right? So that's number one. Now number two, conjugation. Right? The original form may look like not so complete, but then you perform the product of the conjugation, and then it turns out to make it look better. That can happen as well. All right, conjugation for number two. And number three, grouping. For this one, you may just need to move things around, and it turns out to, it may lead to a cancellation that you want. That can happen. So 1, 2, 3, you can try, but once again, as the same as every guideline, sometimes your step can fail. So if number two failed, that's when you need to move to number three right here. Oh, by the way, I'm sorry about the order of this 1, 2, 3. Number two is supposed to be the second item of this slide, but I don't know why it appears on the third one. So let's take a look at number three. Number three is to try different paths. So number one, try substitution. Okay, fail. You got something indeterminate. Then you move to number two. You try to rearrange everything the best that you can, but it turns out that I cannot get any cancellation in my function. So that's when I move to this number three. Try different paths. And this is related to what we talked about earlier when it comes to finding the limits of multivariable functions. We have to check all these directions in order to determine its limits. So how do we do that? We are talking about infinitely many paths. So let's take a look at the first one right here. We need to check them all. We need to consider all the different ways. So let's take a look at the first one where we approach a point with a straight line. Okay, let's focus on the origin here, and we try to approach this origin with straight lines. So here we have the first one, straight line. Okay, and then maybe we have this one too, and this one, and all right, I do not like that, so let me fix this one. All right. All of these are the directions that you can take in order to get to this origin. All right, and in order to scare you a little bit, I add more to stress the importance that we have lots of them to consider. So all of these, we must check them all. The question is, how are we supposed to check all of them? We have so many to do here. So it turns out that we can do that by using a general form of these straight line. And that general form is this equation, y equal to kx, where k can be any values you want, any real numbers. So you have the freedom to change this k. For example, if you set the k to be equal to 0, if k equal to 0, what happens? Then y is going to be equal to 0x, and you get this y equal to 0, and you get this line, right? Y equal to 0. Oh, by the way, let me put the axis right here. This is y, this is x. What about k equal to 1? So if I set k equal to 1 right here, and then I'm going to get this y equal to x, and I'm going to get this direction. Right? So this k right here determines the slope of the straight line, of your straight line. And since k can change values, so you can change the slope the way you want. And maybe one more, k equal to -1, and then you get this y equal to -x. And that can be expressed by this straight line, y equal to -x. As you can see here, this y equal to kx represents all the straight line directions that you can approach the origin. Alright, so let's make a note here. What you see right here is the all directions, all straight line directions, all straight line directions. Of course, we have infinitely many of them, but no problems. K covers that all, covers them all. All right, as I told you, when it comes to directions, not just about the numbers, but the way you approach it. We just did the straight line, but it turns out that we can approach this same point by using something else, like parabola or quadratic or exponential. So let's try parabola here. So this one is going to be parabola. All right, let me save some space. Okay, so we have this y-axis, we have this x-axis, and here we want to approach the same origin, but this time we are going to use parabolic curves in order to approach this point. So maybe it looks like this. All right, and like this, a little bit narrower, okay, and maybe a little bit wider. Okay, so we do the same thing down here, a little bit wider, and same with that. So we want something, some expression that represents all these directions, all these parabolic directions, and that can be expressed by this y equal to, well, x squared with the constant k at the front. All right, let's make a box around that. So y equal to x squared, that is a regular parabola. But with this constant k, this factor k here is going to change how your parabola looks like. If k is large, then your parabola is going to be narrower. But if it's small, then the curve is going to be wider. As you can see here, by changing the value of k, you can change the shape of the parabolas you have. Which means that the expression that you have right here, y equal to kx squared, it represents all parabolic directions that you can take to approach the origin. So let's make a note right here that this represents all parabolic directions that you can take to approach this 0, 0 point. Now, when it comes to using parabolas to approach a certain point, you don't have to use the one that is upward and downward like this. You can use ones that on the side as well. So let's take a look at that case. So instead of having a parabola that is upward and downward, we can have ones on the side, and it's going to look something like this. Okay, we want to approach this same origin, but this time with parabolas on the side. Okay, with this regular one and the narrow one and wider one, and you get my point. We have to consider them all. Alright, now we need to find the expression for these lines, and as you know, this is parabola on the side. It's going to be the inverse of what we just did. So it's going to be x equal to ky squared instead. Alright, and by changing the value of k right here, we are going to include all of these directions. And once again, this is about approaching the same origin. So what you see right here, also parabolic direction, directions, but this time this is on the side. Okay, all right, for this one, up and down. Okay, the question is, how do we use them? How do we use these expressions? Y equal to kx, y equal to kx squared, and x equal to ky squared. We can use them by substitute them into the function, right? If you have some function, put them in, and let's see if it's going to work out. All right. In the end, you may have a conclusion about your limits with these functions, with these expressions. Now, we have talked about number 3, and it turns out that number 3 can fail as well. So you are going to start with number 1, direct substitution. Then you move to rearrangement of the function, and then you try different paths. And if it turns out that 1, 2, 3 fail, then you are going to have to try something else. And this comes number 4 right here. Number 4 right here is other techniques. There are many of them. And the one that we are going to learn about is the Squeeze Theorem. All right? Just one. I want you to keep in mind one thing, is that when it comes to multivariable limits, L'Hopital rule doesn't work. So underline this. L'Hopital rule doesn't work with multivariable limits. Okay, so don't use it right here. Don't use it here. It's not going to make any sense. Okay, now that we know the procedure, we know this guideline, let's use them on some examples.